Welcome students. We want to embark on using Laplace transform now for solving differential equations. So Laplace transform is another technique for solving linear differential equations with constant coefficients. Okay. So what you have is, say for example, you have a u double prime plus bu prime plus cu equals to some function g of t. So Laplace transform is useful in this scenario to solve the differential equation, namely you want to solve for u. In particular, it is useful when the right-hand side of the differential equation is discontinuous. So it's useful when g of t is discontinuous. So such functions often arise in application mechanics and electrical circuits where the forcing function, so g of t, if you remember, when we're doing the motion of spring, g of t is a forcing function. So if g of t function is an impulse function, that means it takes effect only for short duration of time, or it's like a voltage which turns switch on and off, you get a discontinuous function. And we'll use Laplace transform to basically solve these problems. So let's see what the idea is behind this. Okay, so we want to solve a problem, so we want to solve differential equation in time dimension. In the time dimension, right, you have du by dt, right? That is your u prime, and you're solving it in for as a function of t, right? So what you do is now you transform this to we'll transform it to we'll apply an integral, so apply Laplace transform. It becomes now it becomes a problem of solving an algebraic equation in frequency dimension. So you see the whole equation, the differential equation becomes an algebraic equations, right? So in frequency dimension. Now, so now the problem is basically solve. So the problem becomes solve. Then solving is easy. So this is easily solvable. So solving easy, so solve easily. And then what we get is solution to the transformed problem, right? We don't get solution to the original problem, but we get solution to this problem, algebraic problem in the frequency dimension. So solution to transformed problem. And then we'll transform it back using what? Transform back using what? Using inverse Laplace transform, using inverse Laplace transform. And then we get basically solution. So problem solution. So suppose if this differential equation was solving for f prime t or f double prime t, etc., we get solution f of t. Whereas doing directly this way might be difficult, okay? This may be directly doing maybe too hard, okay? So now that we have built so much of hype about Laplace transform, let's see what they are. But before that, we should review something about improper integrals. So one type of improper integral is an integral of form a to b f of t dt, where either b is infinity or a is minus infinity or both. It is defined as a limit. For example, if you have a to infinity f of t dt, this is defined to be limit as a goes to infinity of a to a f of t dt. Right? And this integral converges if the limit exists. If the limit does not exist, then the integral diverges. So let's look at an example first. So evaluate the improper integral 0 to infinity e to the power c t dt. So again, the only way you can approach this is basically using the limits. So this is going to be limit as t goes to infinity of 0 to t e to the power ct dt. That is going to be, since you're using a, let's use a as a symbol there. So this is going to be limit as a goes to infinity. Now what is the integral of this? E to the power ct 0 to a divided by c. So this is going to be limit as a goes to infinity e to the power ca minus e to the power 0 1 divided by c. And now it depends on c, right? So if c is less than 0, let me call this integral I. So if c is less than 0, we have e to the power, we'll get e to the power ct, ca will become what? Will become 0. So that means, so if c is, so let's consider the cases. So I will first deal with the case 1. If c equals to 0, if c equals to 0, then this integral, instead of coming here, because I cannot divide by c, so I should look at the start, my integral I becomes, integral I is 0 to infinity of c is 1. So e to the power c becomes 1, ct becomes 1, so 1 dt, which is infinity, so it diverges. If the case 2, if c is greater than 1, then I equals to limit as t goes to a goes to infinity of e to the power ca minus 1 over c, and that goes to infinity as well, so diverges. Now case 3, if c is less than 0, then I equals to this limit, which is going to be minus 1 over c. So therefore it converges. So this integral only converges when c is less than 0 and diverges in these cases. Okay. Now let's look at the next improper integral, 1 to infinity of t to the power p dt. So again, we are assuming that p is non-zero, right? Otherwise it becomes boring. So now this integral, let's call this integral as I. So I equals to integral. So I should be written as limit. So limit as t goes to infinity 1 to t, sorry, in this case we should use a because a goes to infinity 1 to a t to the power minus p dt. Now this is the case. So now we are, this integral depends on p, right? So let's assume the case p is not 1. So if p is not 1, this limit becomes limit as a goes to infinity t to the power minus p plus 1 divided by minus p plus 1 1 to a, this is going to be limit as a goes to infinity 1 upon minus p plus 1, a to the power minus p plus 1 minus 1. And this is equals to 1 upon p plus 1 minus 1 upon minus p plus 1 if p is greater than 1 and diverges, right? Because if diverges if p is less than 1. Why is that? Think about it in the following way. If p is greater than 1, then this power will be negative, right? In that case, the limit will be 0. If p is less than 1, this power will be positive. So in that case, the limit will be infinity, right? So diverges if p is less than 1. Also, now let's deal with the case when p equals to 1, I equals to limit as a goes to infinity of 1 to a t to the power minus dt, which is ln of t 1 to a limit as t goes to infinity, sorry, a goes to infinity, which is going to be limit as a goes to infinity ln a minus ln 1, which diverges. All right. So again, we are trying to build up machinery around Laplace transform. So first, we are going through a few preliminaries. So a function f of t defined on an interval ab, closed interval ab, is a piecewise continuous if your interval can be partitioned into finite number of points, say a t naught less than t1 less than dot 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 to b, such that f is continuous on each piece. So what you're doing is the following. You have a to b, you are partitioning it to t naught, t1, t2, dot dot dot, and you want that your f is continuous on each of this interval. Okay, so it should be continuous inside. What about at the endpoints? At endpoints, it should have a finite limit when approached from within the interval. That means what? If I approach from here, the function should have a finite limit, right? So an example would be somewhat of this form, say, okay, so this is an example of a piecewise function. Yeah. So basically the idea is f is continuous. So basically the idea is f is continuous except for finitely many or finite set of points at which it has only one kind of discontinuity, which is a jump discontinuity. Okay, so it should only have jump discontinuities at those points. So let's look at an example here. So let's draw this. So for t greater than or equal to 0, it from t to 0 to 1, it is t, which is a straight line like this. There's a hole here and goes 1, 1. Okay. And so this is line t for this part. There's a hole on this part. And from -1 to 0, it is constant -1. So these points are included. So this is -1 until -1. It is like that. 0 to this point. So this function is piecewise continuous. This function, so this function is piecewise continuous. Now let's investigate the next function. So again, the same story. So let's just draw this. So again, from -1 to 1, the function is given by -1. So it's included, so -1. Okay. And from 0 to 1, it's given by 1 by t. So you can see that this is going to be yeah. So it has an asymptote like that, right? Basically, it's okay. So the problem is over here, right? So what is the problem? The problem is at this point here, not a finite limit, not a so not a finite limit as t goes to 0 plus. Okay, so this is not piecewise continuous. Okay, so this function is not piecewise continuous. Now, if you have a piecewise continuous function, you can define the integral as sum of integral at each piece. So suppose f is piecewise continuous. That means there's no option of infinite discontinuities, right? So piecewise continuous with jump discontinuity at t1, t2, tn minus 1 on AB, or for that matter, AB, it doesn't matter, then integral a to b f of t dt is defined to be integral a to t1 plus integral t1 to t2 integral tn minus 1 to b of f of t. So to compute the integral, you can break it into pieces and compute them separately and then add them up. Okay. So for example, let's compute the integral of the following function. So first of all, note that it is a piecewise continuous function. So therefore, here we have -1 to 1 f of t dt is going to be -1 to 0 of f of t dt plus 0 to 1 f of t dt. Now, what is the definition of function from -1 to 0? -1 to 0, the function is defined as -1, and 0 to 1, the function is defined as t dt. So first integral is going to be minus t minus 1 to 0. Second one is t squared by 2 from 0 to 1. The first part is going to be, so this part is going to be half, plus when you put lower limit, you get 1. So this is going to be 3 over 2. Okay. So now let's see why we define piecewise function and so on and so forth. Okay. So now comes the definition of Laplace transform. So what is the definition of Laplace transform? So let f be a function defined for all t greater than equal to 0. Then Laplace transform of your function f is denoted by curly f of t, or by capital F of s. This is another notation. Now the variable will change to s, and it's defined to be 0 to infinity e to the power minus st f of t dt. So this is the Laplace transform. Okay. So note that f of s or is a function right? It's a function after all in a new variable s. Okay, so that's one thing to note. Second thing to note is the Laplace transform operator L takes a function f of t as an input and outputs a new function. Yeah, it is important to see that the output is also a function, right? Outputs a new function so output a new function puts a new function f of s, which is, again, I'm rewriting the definition, but it's a good idea to do that, e to the power s of t f of t dt. Okay, and note that it is, yeah, so this is the Laplace transform. So clearly, so 3, this may not exist for this transform may not exist for all values of s, or for that matter for all f as well. So it is therefore important to ask what conditions should be on f and s to know what conditions on f of f and f of t and s must be, so that L of f of t exists. So existence of Laplace transform. Okay, so first of all, so these are the two properties we need for function to have a Laplace transform. So for any positive number a, the function f of t must be piecewise continuous on 0 to a. That is the criteria, first criteria. And f of t must be less than equal to k times e to the power at for some k greater than 0 and some real number a. Okay. So this is said to be a So f is said to be of exponential order as t goes to infinity. Yeah, that it should not exceed the exponential. So now note that not all, so then the Laplace transform exists and is defined whenever s is greater than a. So example, not all functions have this property. One of the candidate is f of t equals to e to the power t squared. Yeah, it's never going to be less than equal to, it's never going to satisfy this. Yeah, so it increases faster than any k e to the power at. Yeah, for any k and a. That is, f of t is not of exponential order, is not of exponential order. Right. So let's do some examples now. Find a Laplace transform of function f of t equals to phi and state for which value does it exist. So first of all, here f of t is continuous function. Yeah, so you need that it's piecewise continuous. So it is piecewise continuous. And clearly it is sub-exponential, right? So let's compute L of function f of t. So I'm going to compute L of 5 evaluated at s. So this is going to be 0 to infinity 5 e to the power minus st dt. That is going to be limit as t goes to infinity integral 0 to t. Well, we are using t already, so let's use a 5 e to the power minus st dt. Now, when I compute this integral, this is going to be limit as a goes to infinity 5 e to the power minus st over s 1 0 to a. That is going to be limit as a goes to infinity 5 e to the power sa. There's a minus sign here, so divided by minus s minus 1. And as a goes to infinity, this goes to 0. This becomes 0, and therefore we get this is equal to 5. So this 5 has to be multiplied here too. So 5 over s. Yeah. And if s is less than 0, clearly, if s is less than equal to 0, the limit does not exist, right? Right, because this limit is only valid when s is greater than 0. Then only we'll have negative exponent, will go to, this whole thing will go to 0. Otherwise it will not. Okay. So clearly you can see that f of t, which is 5, is continuous, hence piecewise continuous. And f of t, absolute value of that, which is 5, is less than equal to 5 times e to the power 0t. So k equals to 5 and a equals to 0. So therefore, it makes sense, right? Therefore, L of 5 of x exists, which is in agreement with our limit. Okay. So note that. So you can replace this by c, and you will see that it will be C by S. Now let's look at the next problem of finding the Laplace transform for function f of t equals to cos of at. So we have L of f of t, the new variable will be s, is same as f of s, by the way. I'm just rewriting both the notations, is going to be 0 to infinity e to the power minus st times cos of at dt, which again by definition is limit as a goes to infinity of 0 to a e to the power minus s cos of at dt. Now we'll compute this integral using integration by parts. So by parts. So if you do integration by parts, your u is cos of at, your dv is e to the power minus st dt. So integration by parts will give me that 0 to a e to the power minus st cos of at, right? What is integration of u dv is uv minus v du, right? So this is going to be u v. So from here you can get v is e to the power minus st over minus s, and u du is sine at with a minus sign divided by a. So uv minus v du, which is going to be minus of e to the power minus st over s cos of at. So this is your uv minus v du. So v is again e to the power minus st over s times du. So du is going to be minus sine at over a. So let's just compute the indefinite integral first. So this is going to be minus e to the power minus st. So integral of this du. So this has to be multiplied by dt. So du is basically derivative of this. So it's going to be minus a times this guy. Okay. This has to be multiplied, not divided. So now this becomes u v. So u is uv. Then when you add, you get a by s outside, integral of, so minus sign here as well. So this makes it minus a by s integral e to the power minus st times sine at dt. Now I'll compute this integral again and then plug it back. So what is the integral of e to the power minus st times sine at? So again, I can apply uv rule here directly. So u is again sine of at dv is e to the power minus s dt. This implies du equals to cos of at times a times dt, and v is again e to the power minus st over minus s. So our original integral I, so I is e to the power minus st over s cos of at minus a over s. Now the integral becomes so integral becomes again uv, which is sine of at times v, which is e to the power minus st over minus s minus v du. So again, e to the power minus st over minus s times du, which is cos of at dt. So I get I equals to e to the power minus st over minus s cos of at minus a by s. So minus of minus makes it plus. So plus a by s square times sine at e to the power minus s. And then here you have a. So here you should have a. So let's see, what do we get? When we multiply this out, we have a. So we have a square by s square integral e to the power minus st times cos of at dt. Now you see this is same as, this thing is same as your I, right? So when we put it back, what do we get? We get a square by s square plus 1i equals to e to the power minus st over s cos of at plus a by s square sine of at times e to the power minus s. Now when you divide it on the other side, we get I equals to s. So I equals to s square by a square plus s square times e to the power minus s cos of at plus a by s square sine of at e to the power minus st. All right, a long problem indeed. So now if you want to compute this limit, so you have your, let's call this as f of s. So therefore f of s is going to be, you evaluate, you substitute s square by a square plus s square. So f of s is going to be limit of this. So limit as a goes to infinity of this e to the power minus s cos of at plus a by s square sine of at to the power minus s. Limit is from 0 to a. Now let's compute this limit. So limit as a goes to infinity. When you put 0, you get, so when you put a, you get power minus s a cos of a plus a by s square sine of at times e to the power st minus, when you put 0 you get, so this will become 0, right? When I put 0 there, I'll just simply get e to the power minus 0, minus of minus 0, then here I will get I have this, and plus when I put 0, this thing becomes 0, right? Let me just write down anyway, sine of at e to the power minus s times 0. So here we have 0. So sine of 0, here we substitute a. So all these are replaced by a, and then we have. So now note that this becomes, so this part becomes 0. Again, limit as a goes to infinity, this will become 0, this will become 0. You'll be left with what? This is going to be s square by a square plus s square times 1 by s, which is going to be s upon a square plus s square. Okay, so long way. I think the problem would have become simpler if I kept computing the limits on the way. Okay. So now, Laplace transform is a linear operator. What does it mean? If f1 and f2 are two functions, they both exist for s greater than a, right? Then Laplace transform for c1 f1 t plus c2 f2 t evaluated at s is going to be limit as a goes to infinity 0 to a c1 f1 t plus c2 f2 t dt, so sorry, e to the power minus s dt. Now if I break this into parts, you will see that this will become limit as a goes to infinity. Let me break this. So I get c1 0 to a f1 t e to the power minus st dt plus c2 integral 0 to a f2 t e to the power minus st dt. Now if you look at this parts here, combined with the limit will go to both of them. You will see that these are equivalent to, this is equivalent to c1 times L of f1 t of s, and this will be c2 times, because we take the limit inside the c2, so we get L of f2t evaluated at s, and this is valid for s greater than equal to greater than a. So Laplace transform is linear indeed. So for find the Laplace transform for this function f of t v to the t plus cos 2t, and for s values which it exists. Okay. So note that for this, we should know that Laplace transform of e to the power t s is 1 upon s minus 1, and Laplace transform of cos of 2t at s is going to be, let's borrow some space here, is going to be 1 upon, so you see, using this formula, we get s upon s square plus 2 square. So therefore, Laplace transform of f of t is going to be, at s is going to be 1 by s minus 1 plus s by s square plus 4. This is valid for s greater than. So why is that? Because this Laplace transform is valid for s greater than 1. So what is common? And this is valid for s greater than 0. So what is common for both of them is the Laplace transform. So we will use the table for the Laplace transform, although at any point of time you can derive it. Thank you for your attention.